Welcome
to the joy of coding.
Hello, and welcome to episode 371 of The Joy of Coding. My name is Mike Conley. As always, it's so good to have you here. We're going to be live hacking on some Firefox stuff today. I'm really stoked to do that with you. So let's start. I'll start by sharing my screen. Hey, yeah, today is July 3rd, 2024, episode 371. A reminder, no plan survives breakfast. I think I know how today's going to go down, but I could be wrong. You know, I have a sense of what I want to work on, but we might get sidelined or stuck or distracted or all sorts of things might happen, and that's okay. We're going to deal with it as it comes, and who knows, you know? You get to watch me deal with it in real time. That's the first thing. The second thing, the agenda that we're looking at is available to you. So if you're watching this on Air Mozilla or Air Mozilla. If you're watching this on Air Mozilla, check out the details section over there. If you're watching this on YouTube, it's down in the video description, a link to the agenda. If you're watching this on Twitch, it's down in the channel details. And you know, once you see this little spinny spin, if you reload the agenda, you should get the most up-to-date version of it as I update it. Because I might add some things as I'm going on with my stream. Then that's okay. We've got chat happening in Matrix bridged to Twitch. So if you're in Twitch and you're chatting, I should be able to see what you're saying. And if you're in Matrix, you'll see what people in Twitch are saying. If you're on Twitch, you'll see what people in Matrix are saying. And right now it's pretty quiet except for my bridge test, which is fine. It's fine. We're just going to go right for it. So what are we working on today? Well, the last couple of weeks, I think you are aware that I've been working on, with a bunch of other people, this like profile backup mechanism for Firefox Desktop, And we're nearing the end of the first milestone where we've got most things to the point where we can back up and recover a profile. And, you know, we're nearing the stage where QA will be able to like really try it out and find where we've missed some things or find where there are issues. But there's like one major component that's still not finished, and I want to try and do that today. It's not a UI component, it's sort of like back-end support component. And that involves something called OS Key Store and payment methods. And so going into this, I'm gonna spend like 2 or 3 minutes describing what it is that we need to do and why and what it's for, and then we'll go ahead and do it. I've actually written the solution to this already. We can take a look at it. I did that earlier today. I was hoping today we could spend, during the stream, time designing and writing tests, because testing this is going to be kind of interesting, I think. All right. I also want to mention that I have to end precisely at half an hour past the next hour due to a meeting conflict. So I'm going to be doing a hard stop in about an hour and 23 minutes. Sorry about that. All right, let's get going. OS Key Store, what's there to say? So you may or may not know this, but Firefox has the ability to store payment methods. And by payment methods, I mean credit cards. I think there are other, it's called payment methods, I think, in parts of the code base, mainly because in the future there might be other things that are included in storage. But for now, like practically speaking, it's credit cards. You may have seen this feature, and it's not enabled everywhere, I think. But I think most of our locales, credit card autofill is enabled. And the way that works is, you know, Firefox will notice whenever you're filling in a form that has what appears to be a credit card, your own credit card information. And if it notices that, it will offer to remember those for next time so that you can do sort of like easier purchases, easier checkout, without having to have a website remember the credit card. So your browser can remember your credit card information for you, which is great. Now, here's where things get a little interesting. We never want to store the credit cards in plain text on the file system. We never... I'm going to put that, underline that. Never want to store the credit cards in plain text on the file system. Never. So what's our solution to this? Well, you have to encrypt them. You have to encrypt. So therefore, we must encrypt the credit cards and only decrypt them on demand. So only if the user has expressed that they want to autofill some credit card form, they want to edit their saved credit cards, or then we will offer to decrypt that information. Now, how does this encryption work? So this encryption works slightly differently from how I think login encryption works in Firefox. I'm not really up to date on how login encryption works, but I am familiar with how payment method and credit card encryption works, mainly because I helped guide someone through a project last year. I helped a student work on supporting credit card import from other browsers. And it's actually quite similar to how other browsers, specifically Chrome-based browsers, do it. So I don't know who modeled their solution on who. I don't know whose idea it was first, but the idea is very similar. And this is where OS Keystore comes in. OS Keystore is a module. Is a JavaScript module, and it wraps an XPCOM component that is, perhaps confusingly, also called OS Keystore, but within the JS module, the XPCOM component is called native OS Keystore. Bob Bias 2 asks, why would you encrypt logins and payment information differently? It sounds to me like they both ideally want similar levels of security. I think I can't say for certain. I'm not part of like the form autofill or credential management team. But what I do know is that Firefox has been remembering passwords for a lot longer than it has been remembering credit cards. And so I believe the encryption mechanism we use for credit cards is more modern than what we use for passwords. They're both secure, but I think the credit card one doesn't have the same sort of legacy and like sort of the baggage of the existing password encryption mechanism. So there's, for example, no reliance, I think, on NSS to do, at least not for like maintaining secrets. I think that's how it works. But again, I'm not on the credential management team, so I don't actually know the history here. But from an outsider's perspective, who's just sort of consuming these interfaces, that would be my guess, is that, credit card autofill is probably only, like, I don't know how old it is, maybe 5-6 years old. Remembering passwords in Firefox is much, much, much older, probably since Firefox 1 or Firefox 2. I don't remember when it was introduced. And so there's a lot of history and baggage and requirements with password storage in Firefox. Okay, so OS Keystore, it's a JavaScript module. It wraps an XPCOM component that's also called OS Keystore, but within the JS module, the XPCOM component is called native OS Keystore. And how does native OS Keystore work? Well, it uses the underlying operating system, the underlying OS's secret management, secret storage mechanism to hold on to a single secret. So what happens is, like on Windows, we have something called DP API. On Mac OS, we have something called Keychain. Not Keychain, Keychain. And on GNOME Linux, we have something called libsecret. Linux GTK, we have something called libsecret. These are all operating system specific ways of holding on to secrets. Like these are libraries or mechanisms or APIs that are exposed to applications that want to have the operating system hold on to a secret. You're basically delegating the operating system and saying, hold on to this securely. You figure out how to do that, but just securely hold on to this. And if I ask for it back, give it back to me. But, I'm trusting the operating system to securely store this. So it's not going to be in plain text or something. And oftentimes, there are different security characteristics behind each of these, but oftentimes I think one of the primary things that you need to do in order to access what's in the secret storage is to be logged in as the user account that stored the information, or you need to be you need to re-authenticate in some cases. So I think maybe on Mac OS it will prompt you for your user password for your user account anytime there's like gaining access again to the secret. Now, we do not use native OS Key Store to hold on to the credit cards. We don't want to do that. We actually have the operating system hold on to a randomly generated secret. So say you're saving a credit card for the first time. Say you're saving a credit card for the first time. You've never done it before. Firefox will randomly generate a secret set of bytes with high entropy and store it in the underlying secure storage. So it'll be stored in one of these three things depending on what platform you're on. And then anytime we want to encrypt something, say a credit card, you use the secret as the key to encrypt things. So the secret is a symmetric key. So the secret acts as a symmetric key, or the details here are a little lost on me. Either it's a symmetric key or it's used to derive a symmetric key. It's one or the other. I can't remember. But the secret is what is stored in the secure storage, not the encrypted credit cards. So Firefox can then delegate to OS Key Store, hey, encrypt these credit cards for me, this like list of credit card numbers. And then OS Key Store will hand back a bunch of encrypted bytes, and then Firefox can store it. Firefox will maintain, it'll just like throw it in the profile directory. If you have credit cards saved, it's in a file. Credit cards are in a file called autofillprofiles.json in your profile directory. And if you've got credit cards saved, you'll see in that structure there's a credit cards property, and then there'll be an array, and your credit card will be in there, but the raw credit card number won't be in there. Instead, you'll see a base64 encoded string, which is the encrypted bytes. And Firefox itself does not have enough information to decrypt those bytes. I think that's one of the key pieces of information here, is that unless the operating system releases the secret to us, Firefox cannot. It will like forget the credit card number. It will, it had it in memory, but then it like we don't hold on to it. We never hold on to the plain text credit card number except in memory, and then that memory is quickly wiped. So whenever you do want to autofill your credit card information, we get the user's authentication, get the secret, we pull the secret out, and then we decrypt the credit card, and then we forget the secret and we forget the credit card number. That's how it works. I guess you don't use import secrets in Python for this. I don't know what that library is. Is there a secrets library? Python secrets, or Python secrets, simple wrapper for password, configure models. I don't think so. We do not use this, and I don't know what this is, but we do not do that. Okay, so that's how that works. So now we have a this all implies a very interesting conundrum for backups. Oh, it's for high entropy randomization. I think we use NSS actually to generate random bytes. So there is some reliance on NSS here to both perform the cryptography with the secret as well as to generate high entropy random bytes. But we do not rely on NSS to store things. We delegate that to the operating system. So So this all implies a very interesting conundrum for backups. How do you back up credit cards? How do you do it? How do you back up credit cards and make it so that those backups can occur silently in the background, but also so that the backups are portable across devices? Meaning, you should be able to take a backup and move it to another computer, restore, and all your credit cards should be there. So how do we do that unless we decrypt the credit cards before creating the backup? But if creating the backup requires us to ask the user to decrypt the credit cards, and we're doing it in the background, won't that be highly interruptive? Like, you'd be using the browser and all of a sudden it'd be like, hey, unlock secrets for us, please, so we can create a backup. Like, that'd be really unpleasant as an experience, probably be very confusing, and the users wouldn't necessarily understand, like, why is the operating system asking me to unlock security storage, secure storage? So our solution to this was to do the following. When we create a backup, a user can choose to have that backup encrypted or not encrypted. So that's the very first thing. If they choose to not encrypt their backup, we're done. That means we're not even going to, like, we don't store certain information inside of unencrypted backups. We won't store cookies, we won't store passwords, we won't store credit card information. We're not going to store credit cards in it, so nothing to do. If they did choose to encrypt their backup, then what we'll do is, when enabling encrypted backups, is this. When enabling encrypted backups, then ask the user to authenticate to the native OS key store, and we exfiltrate the secret. We get the secret out that the OS has been holding on to, but we then store it in the encrypted backup. Encrypted using using one of the keys derived from the backup password. So at that point, what you've done is you've made the secret, you've taken the secret out of the hands of the OS key store, like the underlying mechanism, and we've jammed it inside of an encrypted backup, but we've made sure that the secret is backed up. This is you can almost think of this as like key wrapping. I'm no cryptographer, but this is effectively key wrapping, where I don't really ever want to see the secret, but I want to make the secret portable. So I wrap it first in something so that it is like an opaque set of bytes, and then only whenever we are doing decryption would we unwrap the secret. And you can only do decryption if you happen to have the user's passphrase. So, note, this is only as secure as the user's backup password. So we need to encourage users to use a very strong one. Now, we've debated this a little bit. The security engineering team would really prefer that Firefox generate a strong key for the user, but we did some back and forth, and what we ended up doing is we thought we'd use the same password characteristics that we use for accounts, because that's already sort of been vetted as like a series, like a strong set of guidelines for passwords. We're just going to use it for accounts because we're trying to reduce how much that users need to kind of remember. But I mean, you could choose to use a very long, you could use like a 25-word passphrase if you wanted. You could use a very, very strong, there's no like limit to the length. You could use like a megabytes worth of bytes as your password if you'd like. And we don't use that as the key, to be clear. Like we stretch the password. We do, I think, 600,000 rounds of PBKDF2 to stretch what we call the recovery code into a series of bytes that we then derive various keys from. And one of those keys is then used to wrap the secrets. So that's the sort of the model that we developed with the security engineering team. And that's the sort of thing that like we're going to have to be audited on. Like the security engineering team is going to be poking at, once we're done our implementation, they're going to be sort of banging the tires on it to make sure it's solid. Maybe you also mentioned of the not encrypted backup that passwords is not stored in the settings. Well, we do. We will mention that actually. If you take a look at one of the builds I've got here, you can see like if the UI isn't exactly, it's not perfect, but like when you're enabling backup to encrypt it, you have to opt in, and then that will back up your passwords, payment methods, and cookies. So then you like opt in, choose a strong password, and then you turn on backup. That's how that'll work. Okay. So that's a lot of talk. Yeah, so we exfiltrate the secret and we store it inside of the backup. Then at recovery time, we create a secondary temporary OS key store instance, and unwrap the original secret, and then use the temporary OS key store to decrypt the credit cards, and then we re-encrypt them using the local OS key store, the one that is used on the current machine. Now, if you're doing a recovery on the same machine, it should be the same secret. So this is basically a no-op. But if you've moved machines, if you've migrated using this backup mechanism, this will re-encrypt using whatever the local secret is on the new machine, which there might not be one, in which case one will be created for you. In fact, I should probably make sure that we cover that case. Do I have... Let me turn this off. I actually need to check out the patch that I've been working on for this so that we can take a look at how it works. And I want to like double check that I'm going to create a secret if one doesn't already exist for the for when we're re-encrypting. Yes, so since I'm using OS Key Store to encrypt, OS Key Store, the module, as opposed to native OS Key Store to decrypt, I'm using the module to re-encrypt the plaintext card. Then it will take care of creating a secret for me. It'll also make sure that the user is allowed to create the storage, meaning that the user may be prompted to unlock secure storage during recovery time, but that's okay. Like that's the worst case was the user is going to be like prompted to access secure storage when we're creating backups at runtime, and we didn't want to do that. So instead, we're sort of delegating it to the very end when you're doing recovery. And when you're doing recovery, having the OS ask you like, hey, can I access secure storage as part of this recovery effort is, I think, a lot more reasonable. At least that's what we're hoping. And after we've re-encrypted the credit cards, then we we basically overwrite the original autofill profiles.json file, and then we copy them into the new profile. So that's how that works. And yeah, that's the long and the short of it. Then we re-encrypt them, then we overwrite the original autofill profiles.json, and then move that file into the new recovery profile. That's how it works. So I've got a patch that does it. Let's take a look at the whole patch. It's not that long. I was very surprised at how easy this was. It's very gratifying because I've been like saving this kind of thing towards the end of the project, this first milestone of the project, mainly because like there was like bigger fish to fry, but I was pretty sure this was going to be straightforward. So it's somewhat gratifying to be correct. Now, I'm not the happiest with the OS Key Store model. Like OS Key Store is not, it has lots of nice properties, but the API is not amazing in that, like, it's not an object. An OS Key Store is not an object that I can pass around. I would much prefer that so that I could make sure to like clean it up when it goes out of scope and stuff. Like I have to do some manual management of that Let me explain. I'll start by looking at the patch. We'll look at it together and I'll explain what I'm referring to. So the very first thing I do is I make sure that the native OS Key Store, the XPCOM component, is something that backup service can access. And then I set up a static recovery OS Key Store label. So there's a thing to know, which is that the secure storage for every operating system with libsecret, keychain, DPAPI, they all expect some kind of like label. They're effectively glorified secure key value stores with like maybe other properties, not just like some key and some value, but like there can be like other rich properties per row, but like effectively it's a key value store for a secret. And we want to have a key in the operating system's secure storage for our temporary recovery OS Key Store implementation. And so the one that's used in OS Key Store is, I believe it is the app base name. So in that case, it'll be Firefox, and then it'll be encrypted storage. So if you're on Mac OS, for example, and you open up Keychain, you'll probably find something called Firefox encrypted storage in there. If you happen to have Opera or Chrome or Edge or something on Mac OS, you'll also see similar things inside of Keychain. I don't know exactly how you access DPAPI on Windows, but presumably you'll, if there's a tool to do that, you'll see Firefox encrypted storage on in that mechanism, and that'll be the one that's used for Firefox. Would have been nice if there was shared secure key handling on all OSs. I mean, this is what we're seeing here is the three solitudes of the desktop operating systems, and there's probably very little incentive from any of them to standardize on this exact same thing. Like, they want to lock you into their operating system. They don't want you to use someone else's operating system. So of course they're going to invent their own thing. And us cross-platform app developers just kind of have to grapple with it. Okay, so going back to the patch here, we set up our label. This is going to be the name for our temporary OS Key Store row in secure storage. I updated a comment here to describe what this method is doing. I wish there was more context here. Let me take it back to the source for a second. Backup service. So in the extract compressed snapshot from archive, what it'll do, so at the point where we're potentially pulling the data out from the single file archive, the backup that's created, this is when we might, decrypt the contents of the backup. The actual file itself is not encrypted. It is a specially crafted HTML file, but the contents of your backup are encrypted. And so we have to extract those bytes from the specially crafted HTML file. And then we do our decryption here. And then in the event that we were decrypting, we will then tell the native OS Key Store, okay, we're going to, I want you to like write into your secure storage for this label, the one that we're setting up for our temporary label, the secret. Like the decryptor will give us back the secret that had been included inside of the backup that was encrypted. So we will do that work. And then we exit. So this is the part I don't like. What I would have loved is if native OS Key Store was like an object that I could pass around and then make sure was destroyed. But instead, it's this like service that is external that I like prepare with this row. It's more of like a database table effectively. And I write into it, and then I have to remember to delete this row when we're done. So we extract the compressed snapshot from the archive. And then here's where I delete it. So after we're like recovering from a snapshot that's been extracted from a backup, at the very end, no matter what, inside of this like finally block, I delete the secret, which is like I'm pretty sure a no op. I need to verify that, but I think in the event that there is no such secret inside of the native OS key store, this is a no op, and I should double check that. It's iOS key store delete secret. If there's no secret with the given label, no action is taken. So it's fine. This is, and maybe if we had decrypted a backup, we would have created the temporary recovery OS key store row with the label key store row with the label backup service, which we will now delete no matter if we succeeded or failed to recover. Note that according to NSIOS key store, this is a no op in the event that no secret exists at backup service.recovery OS key store label. So we're fine to do this even if we were recovering from an unencrypted backup. Okay. Remind me later. Okay. Next, this is the kind of the fun part. Here's where we actually do the decryption re-encryption. I kind of spoiled it because I think we looked at it before. But in the recover method for credentials and security, the credentials and security resource, well, first of all, here's the backup, the backup method, which doesn't do a whole lot. All it does is it just like copies some JSON files, some static files into the staging path, and for these it clones some SQLite databases to the staging path, which uses like the special SQLite cloning mechanism. Recovery is more complicated. Here again, we're reading in the autofill profiles, we read in the JSON, we access each of the credit cards, we find the encrypted one. If we find the encrypted number, we decrypt the bytes using the recovery OS key store label, and then we what you get back when you decrypt bytes is bytes. So we have to turn it back into a string, and that you basically recover the plain text card as a string at that point, and then we re-encrypt that string back into another string, a base64 encoded string, as new encrypted card, and then we poke that into the credit card row, and then that's what we write back out to the JSON file. So it works, and I tested this, and it seems to work. And I need to think about testing now. So that was like 20 some odd minutes, maybe a little bit more like 25 minutes of me explaining what's going on. And now we're at the point where I wanted to get to, which is we need to think about how we're going to test this. Unit testing is like, some of this already smells like it's going to be a pain to unit test, mainly because, you know, I'm calling into this other service from this method. So like, I'm gonna have to like think about that sort of like, do I stub this out, or do I allow it to call into lazy OS key store? I don't want to test OS key store when I'm testing this stuff. I want to make sure that like OS key store is tested on its own. When we're writing unit tests, we need to make sure that, you know, we're testing the smallest possible unit and not like overlapping with pre-existing tests, because that's a waste of time. Now for integration tests, we are going to want to make sure that we're using the real OS key store, and we need to make sure that we don't pollute the system that we run the test on. That is the thing I think I'm most concerned about. Is like when we're running integration tests, or even when we're running real tests, if we're using OS key store, the real OS key store, that means we're talking to the operating system's secure storage, and that means we could accidentally overwrite like on a testing machine, it's fine. Like those testing machines get wiped very frequently. But if I'm like a developer and I'm running this test, I want to make sure that I don't accidentally like blow away the real secret for my production or like my actual user Firefox instance. Like we want to make sure that it behaves correctly. Maybe also check that you never have the secret in clear text. I'm not sure what you mean by that. The secret is only ever, if we go back to backup service, we write the secret, OS key store secret, here. We do it here, and then we never refer to it again. And then, the credit card number. Yeah, I mean, like, we never, we have it in memory here, we re-encrypt it, and we write it here, and then we forget the plain text card. It just gets garbage collected. But probably what we want to do is make sure that at recovery time, yeah, like that we haven't accidentally written a real credit card number in here. I guess that's a good idea. We can start thinking about that as a test. So ideas for tests. So here, I'm just gonna start splatting out some ideas. That's a good one. Making sure we don't accidentally store a plain text credit card number inside of autofill profiles during recovery in this. I need to update the integration test to ensure that we don't accidentally overwrite any real secrets on the machine the test is running on. Overwrite any real useful secrets. So I think that's where I really want to start. So I'm going to put that at the top. I need to make sure that, I mean, the basics. I need to make sure that credentials and security backup resource will do the decryption and re-encryption properly and produce encrypted. I think this is basically a version of this. So produce encrypted bytes for the cards, and like maybe this can be part of that. I think that's really the test, is make sure that it works, like that encrypted cards get transformed. Now this is a little tricky because like make sure this will work if the secret is common between the device that was backed up and the device that was recovered on, or if the secret is different between the two. They'll be common if it's the same device. Like we store, even across multiple profiles, I believe we use the same secret. Like Firefox is just given one secret in the secure operating system storage. So this is what I want to start with. How do I want to do it? Well, let's take a look at the integration test. By the way, base64 is not encrypted, rather encoded, since you don't need a key to decode it. Yeah, where did I say encrypted? I mean, base64, whenever we decrypt the bytes, we get back bytes. We convert those bytes into a string. Whenever you encrypt the plain text card, what you get back is the base 64 encoded encrypted bytes of the plain text string. So I should have been more specific. Yes, base 64 should not be confused with encryption. Base 64 is a way of encoding bytes in a way that is like compatible with, you know, UTF-8 encoded files, or like ASCII. If you need to just like present some bytes or store some bytes somewhere in a file that is expected to hold text, like readable text, you probably want to use base 64. That's sort of like the de facto. There are disadvantages to base 64 encoding. The big one is it inflates the size of what it is that you're encoding. And that's something that we've had to accept as a trade-off here, where, you know, the backup file that we are writing is an especially crafted HTML file, and you can't just store random bytes inside of an HTML file if you want it to be readable by other browsers, or you know, to be interpreted as an HTML file. So we've had to base 64 encode it, and so that, you know, we compress the backup before we base 64 encode it. The way it works is like we compress all of the snapshot, then we encrypt it, then we base 64 encode it in blocks. Sorry, we encrypt it in blocks and then base 64 encode each block. And then when we decrypt, we base 64 decode each block, then decrypt each block, and then reassemble the compressed file, which we then decompress. It's very convoluted, but the nice thing about this is that we're able to store a humongous quantity of information inside of the HTML file. We are quite confident that it is securely stored, and that the HTML file is portable. You can move it between systems. It can go between Mac OS and Windows and Linux, and you could open it up in another browser even. What you'd see in another browser, it's kind of neat, is like if you were to, let me find a backup file. Here's a backup file that I created today with some payment methods. If I open it up inside of Firefox, it looks like this. It's like, hey, here's a backup file that you can restore, and here's some instructions on how to do it. And if you open it up in, say, another browser like Safari or Chrome or something, it'll give you the opportunity to download Firefox to recover from. So that's one of the advantages of the HTML file, is that it allows us to have like a download and install experience on a new machine that doesn't necessarily have Firefox on it. That's the advantage. We can actually use the competing browsers as a runtime to show our backup restoration experience, which I think is kind of clever. Okay, so let's figure out how to test this. Yeah, I wanted to show the integration test. So we've got a lot of tests. This is I'm particularly proud of the testing that we've done for backup. So we have this thing called coverage.moz.tools. Now, to be clear, code coverage is not a you shouldn't always be chasing 100% test coverage. Like, that's not necessarily a useful metric to measure, but zero coverage is a smell, and decent coverage, high coverage, is generally speaking a good thing. If you see 100% coverage, I'm usually a little skeptical. Either what's being covered by tests is either really short, or someone has exhaustively tested everything, and that probably means very brittle tests. But somewhere between like 80 and 95% is like, I'd say, a decent amount of test coverage. And if you take a look inside of components backup, you can see we've got 94% test coverage, which I am fairly pleased about. You know, I don't want to say that that 100% coverage is like, it means there are no bugs. That's not what it means. 100% coverage just means a test ran and these lines were executed during tests. Backup resources, it has zero coverage, but that's just because it's a utility for importing all of the other resources. Right. So where am I going with this? The test, the integration test. Our integration test is under backup, tests, Marionette. We use this Marionette system to write integration tests. What's nice about, you've probably seen me write tests using something called Monkey Test, and these tests are written in JavaScript. There are also XPC shell tests. They're also written in JavaScript. These tests are written in Python, for better or worse. But what's nice about Marionette tests is that it allows us to do something that Monkey tests and XPC shell tests do not allow us to do, which is the harness is separated from the executable that is under test, meaning that we can shut down the browser and restart it. We can change profiles on it. And that's something that backup and recovery in particular does. So Marionette is an obvious choice for our integration tests. Okay, so this is not a very pretty test, to be clear, but I'm going to talk through it. So we do a lot of setup, and we add a bunch of like testing information. We try and like dump enough information inside of the profile that's going to be backed up so that we can verify that the recovered profile also has that information. This is, I think, a lingering leftover that I have a patch somewhere that removes it. So we can ignore this part. This is the recovery code that the test uses. And this is fairly interesting, where when we create the backup, we don't want to, in this Marionette test, actually include the user's real OS key store secret inside of the backup when they're running just the Marionette test. Like, we don't want to do that. So what we do is some hackery. Oh, that would also show an OS authentication dialog if we were to try and access the user's real OS key store. So what we do is we remember the original label that OS key store uses, and then we generate a random OS key store. We enable encryption, which is going to do the job of exfiltrating the secret for OS key store. And then we clean up and we put the store label back. So what we end up doing is I'm just realizing now, we generate a random OS key store and then we clean it up. And we're going to need to make sure that not only do we use this random OS key store when enabling encryption, we also want it when we insert credit cards. Do we do that anywhere in here? Payment? No. We don't currently store credit cards, mainly because the OS key store stuff wasn't done. So now we need to kind of think about this a little bit. So this sort of setup, I think, actually needs to occur earlier, or we need to run this routine, or like the inserting the payment methods routine in here. I'm going to opt for readability. And so what I'll do is I'm going to add a comment. We want to make sure that any payment methods in this testing profile are properly encrypted using OS key store, and that the encrypted backup will properly extract and recover from the original OS key store secret. What we don't want is that maybe use get random values instead of math.random. To be clear, yeah, I'm using math.random here, not because I'm trying to do anything cryptographically secure. I'm just trying to create, like, it doesn't matter that this is somewhat predictable. The label is not a thing that we need to keep secure. It's just something that we want to have a high degree of certainty that there isn't going to be a collision for the label. That's all we're doing here. Yeah, you never want to use math.random for like generating high entropy secure bytes or anything. That's you want to use get random values instead. Good call, Smurf D. Hang on, my phone is blowing up. What's happening here? Okay. Looks like I have some reviews to do. Okay. What we don't want is to do is encrypt or extract the OS key store secret used by this machine's actual Firefox instance, if one exists, since they're all shared. We also definitely do not want to accidentally overwrite that secret. Okay. So we solve this by tricking OS key store by poking some values into OS key store .sys into the OS key store module, poking a new store label value into the OS key store module when we do the following, before we do the following. Store credit cards, store payment methods, enable encryption. Once those two things are done, we can put the we don't even need to put the store label back. We don't really need to worry about putting the store label back afterwards, since the process will end shortly. The browser process with the temporary store label will end shortly. Oh, but we do want to delete it. So actually, we don't want to pollute. We also, once that's done, we delete the temporary OS key store row that we created. I think that's what's happening here in cleanup. Cleanup. Yeah, it deletes the secret. Okay. So what I'm going to do is I'm going to say execute script This is how apparently this is how we run like privileged JavaScript within our test within the browser that's running. It's quite awkward. But we're going to import OS key store. We're going to do this stuff. I'm going to take the top part. This technique is similar to the one used in OS key store test utils, which is unfortunately not a module that is available to Marionette tests. Right? Isn't that what's called OS key store test utils? Yeah. We don't really need to remember the original store label. That's the thing we don't need to do. We don't need to put the OS key store label back. So we can just do this. And then we need to remember to do this. Script. Oh, Python. Outer resolve. Execute async script. Then we do this sort of weird dance. We don't need the recovery. We don't have a recovery code argument. We just have outer resolve. Then we do this dance. Then outer resolve. Right? Something like that. Right. And then in between here, we need to, actually I'm going to move this down, enable encryption, and then it creates a backup cleanup here. Now we clean up our temporary OS key store from the OS's secure storage. We won't need it anymore. So then we're going to do self add test credit cards. Test, or I'll say payment methods. Now that we've got the fake OS key store set up, we can insert our testing payment methods, which will be encrypted by it. Okay. Then we run the encryption, we clean up, and then we do this part again. We generate another one and we recover from the backup archive. That should still work. I don't think we actually need to do this part. So now what we need to do is we need to insert credit cards. So add test payment methods. So under, where would that be? Add test form history. It's not exactly the same thing. It's add test permissions. I'll just add a new one here at the end. Def add test payment methods. And then I'll have a verify payment methods. Verify recovered payment methods. Okay. So we'll make sure we call this. That happens right here at the end of the... This is a very long, complicated test. Self.verify recovered payment methods. All right. So what we're going to do is we're going to execute an async script that will insert some credit cards. Was it history exists? That's under verify. This is what I want. I want something like this. But instead of using places, I'm going to insert some credit cards. Now, let's look at an example of doing this from the migration wizard. Insert payment credit cards. I guess we called it credit cards in migration utils. Oh joy. Okay, so we create an object and then we called insert credit cards wrapper, which is really a thing that just makes sure that form autofill storage is initialized and then it adds credit cards to each. So we'll do basically the exact same thing. We're going to const form autofill storage and then inside of our promise here we will initialize form autofill storage. I'm pretty sure it's already initialized elsewhere for other things, but I think it's good practice just in case we decide to disable one of those other tests for during development, that like, because this is it's what's called idempotent, meaning even if you call it multiple times, it'll only ever happen once. Idempotent. Denoting an element of a set which is unchanged in value when multiplied or otherwise operated on by itself. An idempotent element. Yeah, an operation can be applied multiple times without changing the result. It's a very wordy way of saying it runs once. Idempotent. Okay, so we initialize form autofill storage, and then we're gonna say await. We're gonna add a credit card, and our credit card will be something that looks like this. CC name. The name will be Boston Low. No, who will I name this? What will be my name? Foxy the Fox. Foxy the Firefox. CC number. So I need to put it in plain text here. There are test credit card numbers that I know are valid. These are them. So we're going to use the MasterCard one. Foxy uses MasterCard. That's not an endorsement. CC exp month. We're going to give it a month 5. CC exp year. I think it's 4 digits. Yeah, 4 digits. Thank goodness. It may accept 2 digits, but we're gonna inject 4. We'll say this thing is good until 2099. Woo! So we're gonna insert that credit card, and then when we verify, how will we verify? We need to query credit cards. Credit cards. Storage.credit cards. Get all. Await. So let cards equals form autofill storage credit cards dot get all. And then if I'm gonna do it this way, like card. If not card, script, return false. You know what? I think we can do better. Cards, if not cards dot length. If cards dot length is not equal to 1, return false. Let card equals card 0. If card dot cc name is not equal to Foxy the Firefox, return false. Unfortunately, we don't have the nice assertions in Marionette inside of these scripts that I'd normally use in tests. Otherwise, I'd use those, but here I'm just going to use equalities and a true or false. If card cc exp month not equal to 5, false. If card cc exp year not equal to, I actually think these are supposed to be strings, not numbers. CC exp year. Looks like it can accept both, but I'm going to use strings. 5, 2099, return false, and otherwise return true. And then we're going to say card exists. Equals that. And then assert true, card exists. Okay, so we'll insert the card, and then when we're done recovering, we'll verify that the card properties all match. When we pull this now, let's run this again, or think about this again. This verification needs to occur. Oh, yeah. Okay, so. Oh, okay. we need to make sure that these share the same OS key store label, because it would have been encrypted using this one. So I'm going to say OS key store label is going to be a thing that we return. We're not going to clean up. Return. Key store label. So we get back the OS key store label. And then print persisting OS key store temporary, persisting fake OS key store label. Okay. Then we quit, we launch. Return that encryption is enabled. And then we need to clean up. Clean up the temporary OS key store label. Script args. Key store label. And then in here, arguments. What we do is we say import OS key store. And then do what we did before, test backup.py. OS key store.cleanup. We'll do OS key store label. Equals OS key store label. And then we'll do an await cleanup in here. And that occurs after we verified these things, so we won't need to get any values there. I think that's it. So let's run through it again. We start the browser. We inject a bunch of stuff, including, oh, we got to add test payment methods. We add our payment methods. Oh, no, we don't do that here. We don't do that here. We do that here. So first of all, we set up our fake OS key store. It's fine that we forget that this is a random one. We're gonna, that's okay. That's actually best. That means it's not gonna share it with the other one that we create. We add our payment methods. We then enable backups or enable encryption. So our OS key store secret from up here gets stored in the backup. We create the backup, then we clean up our first OS key store. Then, upon recovery, we launch a new browser. And then we import OS key store. We write a different store label in there, and then recover from the backup archive. We then launch that backup, that recover. Then we launch the new profile. And then we verify that the payment methods are still there. And then we clean up the old, the second temporary OS key store, the fake one that we created. And then we're done. Okay. That seems to make sense. I'm a little scared, but let's see what happens. Mock, test, browser components, backup, test, Marionette, test, backup. Here goes. Well, actually, before we do that, let's lint, mock lint, outgoing fix. Just in case there's something wrong with our Python. Okay, no problems. It ran, so I'm just to double check. Mock, lint, browser components, backup, tests, Marionette, test, backup. Isn't anything in there you don't like? Oh, see, it, yeah, there we go. Fix it. Okay. Now how do you like it? How do you like me now? Okay, let's run it. Mock, test, browser components, backup, test, Marionette, test, backup. Fingers crossed, gang. Here we go. So we inject all of our stuff. I'm going to create a backup. Oh, that's not a good sign if it's just sitting there. OS key store not defined on line 122. Okay, we're going to quit. Line 1, OS key store not defined on 122. Did I use it before I'd imported it? Oh yeah, in here to clean up. I didn't clean up properly. So I need to bring this down here again. So I'll have to clean up my own machine. All right. Did I do that anywhere else? Key store. No, I think I'm okay. Let's try it again. Okay. Launching. Stuck again. Could not create recovery profile. Why not? Line 190. Cover from backup archive. Did I change the signature here? No, it should return this. Let's recover from snapshot folder. Oh yeah, hang on. I've changed the signature of this accidentally. I should return. Whoops. Okay, so let's try that again. That's why you test. Okay, no good. Syntax error. Missing a bracket after a condition in line 246. So in some of my JavaScript. So down here, I'm missing a close brace. So I have to like parse this manually. Missing a close brace somewhere. This is so silly. Is it here? No. If I just like try and paste this inside of a JavaScript terminal, what would it say? Okay, it still doesn't like it. So this is invalid JavaScript on line 25. So 25, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. Ah! I see it. So dumb. So dumb. I wish we had better syntax highlighting in there. Or like I do wish a better experience writing marionette tests. Unfortunately, we don't live in a perfect world. Okay, false is not true. So we verified recovered payment methods. Here's what I'm gonna do. Get all dump cards. JSON stringify cards null. Plus gecko log dash. Okay. String literal contains unescapes. Let's just do that then. Creating so much garbage inside of keychain and my profiles directory probably. Okay, cards. I think I saw it. Where did I see it? Cards. The empty string. Or the empty object. So interesting. Let us now do some more logging. We're gonna credentials, resources, dump read in records from user profile. JSON stringify autofill records. Found an encrypted card. Decrypting with old secret. Did decryption. Re-encrypting. Dump final credit card. Object. JSON stringify credit card null. And now if we throw, I'm gonna wrap this in a try catch. E dump rut row e dot message. E dot line number file name plus e dot line number plus. All right. It's a little printf debugging. Let's go. Time. Oh, thank you very much. Thank you, Smurf D. You're the best. You saved my butt. Thank you so much for watching episode 371, I think this was, of The Joy of Coding. Let me know what you thought. We're done here. There's a forum at the bottom. Let me know what you thought. I'll drop a link. Rate this episode. I'm putting the link in the chat. If you want to rate this episode, let me know what you thought. That's a great way to ask me questions as well if you want to ask me questions. And I will hopefully see you next week with episode 372. Thanks again for watching, everybody. Have yourselves a great week, and I'll see you soon. Take care. Bye-bye.
The joy of coding.
See ya.